Hey folks, it's Mr. Glover here. So today we're going to tackle the last section out of chapter 7. So it's the last day of new material on logarithms. Um, the topic of today is called the natural logarithm, and the idea is that it's going to be we're going to define a special number. That special number is going to be something like pi that's irrational that is going to end up being a really common number that you will see a lot if you study more math. And the idea is that it's going to be a base of a logarithm. So we've had things like log base 2, log base 3, log base 4. Well, we're going to define a new number, and that's going to become the specific base of what's called the natural log. And we'll go into why you might want to use this versus other types of situations as well. But that gives you an idea of what we're going to do. So to get started, let's think of a specific example, and that example we're going to think about is compound interest. And the thing that we're going to change with the compound interest formula is going to be the compounding periods. So I want to kind of go back to this idea of what a compounding period is. So when we talk about finances, a compounding period is like a period of time that after which the compound interest can be applied to your bank account's balance. So let's say that you had, we'll keep the number simple. Let's say you had $100 and you were making 5% interest once a year. If you had a compounding period of annually, what that means is one time per year, the bank calculates 5% of your 100, which is $5, dumps that back into your bank account. However, if you split the compounding periods up, if you split it up into larger or smaller intervals, like monthly or weekly or daily, then rather than waiting till the end of the year to get your interest payment, you're going to get an interest payment after every month or after every week or after every day. And the reason why this matters is because the subsequent payments, so the next payment, your interest is going to be calculated based on your principal of 100 plus your accrued interest. So the more often you get interest, the more interest you will make because you're making interest off of interest you previously got. It's kind of a weird concept, but it's very important in the world of finance. So we're going to kind of look at this, and we're going to go to extreme examples, and we're going to see what happens when we change our compounding periods. So to keep the numbers easy, imagine you had $1 to invest in an account that pays 100% interest annually. Let us consider the value of your investment after a 1-year period with different compounding periods. So if we were compounding annually, we would have the formula A equals $1 times 1 plus I over N. I is 100%, so I is 1 divided by N, which is 1. And this is to the power 1 times T, and 1 year is 1 times 1. This just equals 2. So at the end of 1 year, you have $2. And that makes sense. You started with $1, you got 100% back. $1 plus $1 is 2. What happens if you compound semi-annually, though? So you get half of your money halfway through the year, and then you get the rest of it at the end of the year. In this case, we're going to use A equals 1 times 1 plus 1 over 2. N is 2 this time, to the power 2 times 1. And what this does is it changes your investments. Instead of $2, it's now $2.25. So you've actually made 25 cents more. And we can keep changing these numbers. I'm only going to go through maybe one more calculation. So for the next one, A equals 1 times 1 plus 1 over 12, power 12 times 1. That means you're getting a monthly payment from interest. That is going to result in $2.613. 2.61. You can see that the amount of money you're gaining is increasing because the more frequent compounding periods you have, the more often you're getting interest. So let's change this and go to extremes. Let's go, we'll investigate biweekly, weekly, daily, hourly, and we're going to even go into every second. And we're going to see whether you can just compound more frequently and make more money, or whether there's going to be a limit to how much money you can make. So if we compound biweekly, that's going to result in a final value of $2.66. If we compounded weekly, that's going to result in a final value of $2.69. Daily, 365. That's going to result in compounding periods of $2.71, or compounding periods of future value. And if you compound hourly, that's 8,760 times a year. You're going to end up with 272. So now, and I guess we should have been a little more precise here. This should be n equals 365. This should be n equals 52, etc. It looks like there's going to be a limit here. We saw a rapid increase from 2 to 225 up to 260, then to 266, 269, 271, 272. So as we're going up in compounding periods, 365 up to 8,760 is a lot. We're not seeing the profits scale to the same amount. So it looks like we're getting diminishing returns. Let's go to an extreme case. Let's compound our interest every second. And this isn't something that banks are going to do, but it is something that theoretically is possible. We would be following the formula A equals 1 times 1 plus I, which is 100%, so 1, divided by N, which is 31,536,000. All to the power NT, which is 31,536,000 times 1. So if we compound it every second, we're going to get 2.7183. And technically, this will keep going. Compare this to 2.72, and I'm going to say this was rounded. It probably wasn't exactly 2.72. We're not getting much further. All that's changing are our later decimal places. So it appears that there's a limit on how much we can gain from increasing the compounding frequency. In fact, when n approaches infinity, A approaches 2.71828. That's a special number. This is called Euler's number. And it's denoted with the letter E. It's a lowercase e. So this is kind of like pi. This is an irrational number that comes up a lot when you're talking about exponential growth or decay. And by definition, what we've kind of defined it as is it's kind of like the rate of growth for a continuously growing object. So the reason why it's continuous is that you've got this idea that under normal compounding interest periods, your interest is kind of divvied out in chunks. You reach the first compounding period, calculation is done, there's your interest. You reach the second compounding period, calculation is done, get your interest. So you can split the year up into these kind of intervals, or these days that you get paid in. Those are what you call discrete. Those are specific days that you can break it down. You can actually plot every single individual day. If we continue to increase the compounding period to the point where it's happening so frequently that we can't really split it up into an individual second, because it's happening more than every second. It's technically happening infinitely many times per second. That's what you call a continuous idea. It's not discrete anymore. It's not, you can't schedule the interest payments because it's literally happening at all times continuously. This is the growth, or the base growth, of a continuously growing object. And it turns out that we can define it, or we can calculate it, by just changing our compounding periods to infinitely many per second or per year. It's a special number, much like pi. It's defined as the limit as n approaches infinity of 1 plus I over n to the nt, but that's not the only way to define it. And if you go and take much more mathematics, you will see this number a lot. This number is involved in solving quadratic equations that don't necessarily have answers. There's going to be applications in what are called imaginary numbers. You use this a lot anytime you're doing exponential growth or decay, because it turns out it's actually a very convenient way of modeling things. All right. For now, let's focus on sort of what the number is, and we'll talk about some situations where we can use it, and we're going to define a new logarithm. So, coming back to this compound interest problem, we can actually redefine the compound interest formula, A equals A naught times 1 plus I over n to the nt. We can take that entire formula, we can model it using A naught, A equals A naught. Let's write this a little nicer. A equals A naught times E to the kt. This is a more elegant equation. This is a growth equation. So this is this formula can be adapted to model any kind of exponential growth or decay, specifically continuously growing things. So things like well, bacteria. When bacteria multiply, that's happening continuously. It's not like every hour they decide to spit out a bunch of new bacteria. It's constantly happening. Things like population growth or decay. Technically, it's discrete because, I mean, there's not infinitely many people being born or dying at a given time, but it's not going to happen in nice intervals. It's going to be continuously changing. You could use it to model things like half-lives. You can use it to model a lot of situations. So in this formula, A naught is going to be your initial amount of whatever it is you're modeling. So I'm just going to call it the initial amount. K is what you call the growth factor. And the growth factor is what's going to dictate whether you've got exponential growth or decay. We're not changing the base anymore, we're changing the exponent, and the exponent is going to tell us whether or not our function is going to rapidly increase or whether it's going to rapidly decrease. And then there's time. T is going to be our time period. All right. The function can be used to model anything under constant growth or decay. K is greater than 0 is going to be the situation where we have exponential growth. While K less than 0 is going to be the situation where we have exponential decay. So then the question is, how do we find K? K is going to be what's important in modeling. So we're going to need to have a process for solving for K. And it turns out that we can use the log laws to find this. So I'm going to zoom in a little bit. I'm going to start out with the general form of our equation. Let's maybe do this in blue. A equals A naught times E to the kt. All right. I'm going to take the log of both sides. Actually, before I do that, I'm going to move A naught. I'm going to have to divide it. So A divided by A naught equals E to the kt. All right. And now that we have one term on the left and one term on the right, let's take the log of both sides. So log of A over A naught equals the log of E to the kt. And now I'm going to take a special base log. I'm going to take log base E. On the right-hand side, log base E of E is just going to turn into 1. So kt, let me just rewrite this, log base E of A over A naught is simply going to equal K times T, because log base E of E cancels, and you were left with 1. So we're almost done. If we want to solve for K, we just need to divide by T. So log base E of A over A naught divided by T equals K. This is a formula that we can use to calculate K, and we only need to know 3 things. We need to know the final amount of something, we need to know the initial amount of something, and we need to know the time that it happened in. And oftentimes we're going to use time as years, but it really doesn't matter what you use for time as long as you're consistent. So if you use years when you're solving for K, well, then you need to use years. You need to use years when you're solving for final amount. If you're modeling something that happens really fast, like bacteria growth, maybe T is seconds. When you go to use your equation to solve for final number of bacteria, you need to remember that T is seconds. So it's a very, very open formula, but that means you have to be careful in how you apply it. This leads us to the next definition, which is the natural log of x. So the natural log, which is often called ln, ln, It stands for the natural logarithm. It is just a logarithm with a different base than 10. So it's literally just a log with the base e. So it's base 2.7. I shouldn't say that because it's not exactly, but it's roughly that, rather than base 10. Otherwise, all log laws apply, and the algebra is exactly the same as a normal log. It's just a different base. And there's actually a button on your calculator. You might not know this, but if you go to, it's just underneath log, it's ln. That's the natural log. You can calculate the natural log of any number. And if you use second behind ln, there's e to the x. So log and ln are now both part of our toolkit. I probably don't, well, if you're dealing with expressions like, let's say you're studying physics, and there's going to be expressions with powers of e, you probably want to pick the natural log when you're doing algebra because it's going to cancel nicely. If you're dealing with powers of 10, you probably want to pick log base 10. So it just allows us to pick a log that allows our equations to be more simple, or easier to solve, I should say. You can actually get away without using ln almost ever, but it's going to make things slicker and faster in a lot of cases. So let's try some questions. Solve the following exponential equation. 9 over 11 equals 6 to the power e over 5x. Okay, so first thing I'm going to do is I'm going to divide both sides by 6. I want to remove 6. Okay, so if we divide by 6, this equation turns into 9 over 66 equals e to the 5 divided by x, all right? And now I'm going to take the log of both sides, but I'm not going to take the normal log. I'm going to take the natural log. So ln of 9 over 66 equals ln of e to the 5 over x. The reason I'm doing this is because ln is base e, and I can now cancel out my e on the right-hand side. So I know that ln of 9 over 66 equals 5 over x. I can now multiply by x and divide by ln. And maybe I'll do that in 2 steps. So x ln 9 over 66 equals 5, or x equals 5 divided by ln of 9 over 66. So x is going to equal negative 2.51. By the way, I think I've probably told you this before, but I like to try to point out some tricks if I come across them. So if we get to this point and you need to solve for x, but x is in your denominator, this happens a lot. What you can do is just switch x with whatever term is over here. It'll only work if you've got one expression. So if you had like a equals b over x, you can simply switch a and x, and you can say x equals b over a. It comes from multiplying by x and then dividing by a. But we could have done this in one line instead of 2 extra. So it's a trick that you probably will pick up over time, but it'll save you a bit of time. Okay, let's try another one. This one we're starting in log form. So we need to use our log laws to join this together. We're subtracting logs, so we need to divide their arguments. So we can write this as ln of x plus e over, maybe I need to rewrite this, ln of x plus e divided by x minus e equals 1. All right. And now I'm going to convert this into exponential form. What that means is the base of this log to this power has to equal the argument. So x plus e divided by x minus e equals e to the 1. All right, so now we need to solve for x. I'm going to multiply by x minus e first and foremost. So x plus e equals e times x minus e. That means x plus e is going to equal ex minus e squared. We can now move all our x's to one side, and we can move our things that aren't x to the other side. So let's move all the e's to the right or the left and all the x's to the right. So e plus e squared equals EX minus X. I've just subtracted X from both sides and added E squared to both sides. I need to solve for X, so I need to factor it out of the right-hand side. The left side stays the same, E plus E squared equals X times E minus 1. And that's because X times E gets me EX, and X times minus 1 gets me negative X. And now we're almost done. We just need to divide by E minus 1. So E plus E squared divided by E minus 1 equals X. And then X is equal to 5.88. Now, you can solve this equation without ln. You do need E because it's in the equation. It's kind of like having pi, but you can solve this using regular logarithms. The problem is that you are going to have trouble. Your equation is going to look much uglier because e to the 1 doesn't simply, what am I trying to say here? You won't have this power of e, you're going to have a power of 10, and things aren't going to cancel as nicely. You're going to have a much bigger, uglier expression, but you can do it with other logarithms. You don't need to always use ln. But if you see an e, probably need to use ln. Let's try another one. Solve for x. So ln of x minus 1 equals ln 2 plus ln x. So I'm going to try and join the right-hand side together. Ln of x minus 1 equals ln, oops, I was actually going to write LON, ln of 2 times x, and that's the product rule. And at this point, I can kind of scrap the fact that I'm dealing with ln, because one logarithm equals another logarithm. That tells me that the arguments have to be equal. Technically, we're going to be putting each side to the power, or as a power of e, but the result is that we can just disregard anything other than the arguments because they must equal each other. X minus 1 has to equal 2 times x. So now we can rearrange this a little bit. I'm going to subtract x. So minus 1 equals 2x minus x, or negative 1 equals x. So this is no different than what we did last chapter. It's just that now we have a different base log to do it with. All right. So now that we've done problems that involve rearranging equations, let's do a problem that involves modeling. So now this is a hard question. This is about as tricky as it's going to get. But this is a great question because it's real world. I don't know if these numbers are exact, but it gives you an idea of a real world problem where you would want to use this to model growth. Honestly, right now, you're probably going to use exponential growth to model things like infection spread with COVID. Things that involve spread or growth are going to be modeled using exponential functions. So let's try this question. In January of 2019, the population of Venezuela was estimated to be 32.6 million. It was estimated that 10% of the population had emigrated from the country between 1999 and 2019. Suppose this trend continues. A, find the growth factor K, model the population. B, use your function to estimate the population in 2034. And C, to the nearest year, when will this estimated population be less than 30 million? So let's list out what we know. We've got quite a bit to unpack here. Okay, so in January 2019, the population was estimated to be 32.6 million. Okay, so in 2019, A equals 32.6 million. And I know that this is 90% of what I had in 1999. And that's because 10% population has emigrated. So in 20 years, population decreased by 10%. Okay, so what I can do over here is I can sort of write A naught is going to be my population in 1999, and A is going to be my population in 2019. I know that A equals, sorry, let me write this again. I know that A times 0.9 equals A naught. What that's saying is that my population in 2019 is 90% of my population in 1999. It's like a 10% decrease. So if I want to find what my my population was, I just need to divide by 0.9. Or actually, I think I have these written backwards. Yeah, I did. Sorry about that. A naught times 90% is A. That the way I had it written before was saying that we've actually grown in population. The way I have it written here, A is 2019, A naught is 1999. If we multiply our population in 1999 by 90%, we get our population in 2019. So what it all boils down to is our initial population is going to be our final population divided by 0.9. Or our initial population in 1999 is going to be 32.6 million divided by 0.9, or it's going to be 36.22. Okay, so we now know our population initially was 36.22 million. We know our population in 1999 was 32.6 million, and we know that time is 20 years. T is 20 years. So let's write this over here and let's solve for our constant. So we know A naught is 36.22 million. We know A, which is our final population, is 32.6 million. Oops. And I know T is going to be 20 years. All right. So I'm going to write out the compound, or sorry, not compound interest. I'm going to write out the exponential growth formula, and we're going to solve for K. So our formula is A equals A naught times e to the kt. And we need to solve for K, so we're going to basically be doing what we did on the previous page. A over A naught equals e to the kt. Take the ln of both sides. Ln of A over A naught equals ln of e to the kt. What that means is ln of A over A naught equals kt, or ln of A over A naught divided by t equals k. This is the formula we derived on the page that we defined this equation. So we've already got this formula. It's right here. But what I would rather see you do is I would rather see you derive this formula rather than just memorize it. Because if you memorize this and you make a mistake, your question's no longer going to work. If you start at the starting point and you derive it, then you're more likely to not make a mistake here. Technically, if we're not doing tests right now, you can just take this formula, copy it, write it out, and skip 4 lines. But it's a good practice to start with your base formula and show all of the steps in getting your answer. So we just have to put in our numbers. So ln of A, which was our final population, 32.6 million. And now I could write this as 32.6 million, but since they're both in millions, I don't have to actually do that. I'm just going to leave it as 32.6 and 36.22. We will get the same ratio of 32.6 to 36.22 as we will 32.6 million over 36.2 million. So that's completely up to you. Our time interval is 20 years. We're keeping it in years, so that's our scale. If we wanted this to be in seconds, we would have to figure out how many years or how many seconds 20 years is and divide by that. Equals K, and we're going to get a growth factor K of minus 0.00526. Okay, so what that means is that we have a negative growth factor, which makes sense because our population's declining. Over time, we are going to see our population decline. All right, so we've now calculated K. That's A. That's question A. B, use your function to estimate the population in 2034. So let's split the page up. I'm good. We have 2 more questions to do. Okay, so in 2034, we need to figure out how many years it's been since 1999. So T is going to equal 2034 minus 1999, which is going to be 35 years. So let's list out our variables here. We know that T is 35. A naught is going to be 32 or 36.22. And A is unknown. We don't know what the population is going to be. But we do know our growth factor, K, is negative 0.00526. So we can plunk these variables into our formula and we can estimate the population at a given time. So our formula is A equals A naught times E to the KT. Fortunately, we're already solving for A, so we can just leave everything as is. We put in our numbers. A naught was 36.22 million. I'm going to leave it as 36.22, and that way my answer is going to be in millions, times E to the K, which is negative 0.00526, times T, which is 35 years. This boils down to 30.13 million. Now, we should expect that this number is lower than our population was in 2019, and it is. The population was 32.6, and now we're down to 30.13. So you might be asking, well, why are we using this formula? Why don't we just use like a population growth? Why don't we just call it 0.9 to the power t? The problem is that that 0.9 is not every year. That's happened over an interval of 20 years. So we don't have the exact amount that things have changed every year. We could try and calculate that, but this is a simpler way of modeling it. All you need to know is the final value, the initial value, and the time period, and you can calculate a growth factor. All right, let's do part C. So what was part C? To the nearest year, when will the estimated population be less than 30 million? Okay, so what we want to do is we want to figure out when does it hit 30 million. We want to solve for time, and then we need to figure out what year that happens in. So we're going to have variables A naught equals 36.22. That's in millions. We have A, our final population of 30.0. It's just 30. Technically, it'll be any time after this day that we reach less than 30 million. We know our growth factor. K is unchanged because K is attached to this population now. Growth factor is minus 0.00526. And what we want to know is, what is T? So take our formula, start by writing out the formula. So A equals A naught times E to the KT. And we're interested in finding time. So I'm going to rearrange the formula and solve for time. A over A naught equals E to the KT. Take the log of both sides. So ln of A over A naught equals ln of E to the KT. We can cancel out E and ln. So ln of A over A naught equals KT. And then lastly, we need to divide by K to solve for T. So ln of A over A naught divided by K equals T. Put in our numbers. Ln of A, our final population is going to be 30. A naught, our initial population was 36.22. K, our growth factor, is negative 0.00526. And then we just have to put that in our calculator. What we end up with is 35.82 years. if we add this to our initial starting point, so 1999 plus 35.82, that's going to get us 2034.82. So now we have to remember the context of the question. 2034 is not going to have a population of less than 30 million until we get past 0.82 of a year. So if the question's asking us to the nearest year, when will the estimated population be less than 30 million? Well, the population will be less than 30 million after 2035. Technically, if the question wanted us to be more specific, we could multiply 0.82 by 365 days, figure out the day in the year that it happens on, and we could provide like a calendar date. It's 82% of the way through the year. We're probably talking somewhere in September of 2034, but we only need to the nearest year, so this will be fine. So that gives you an example of a challenging question that models population growth or decay using a continuous function of an exponential function. So this is an excellent question. I know you probably don't agree. Many people probably aren't thinking this is that excellent, but it's a great question because it's real. The numbers very well could be accurate. I don't think they are, but they could be. We're answering an actual question that people are interested in. And when we're all said and done, we've got a formula that we can now use to model the population, and we can use that to find a lot of info. We can use that to find out or to estimate what's going to happen in 50 years from now. We can estimate what the population was at a certain point in time. If we go outside of our range of values that we know, so if we go outside of our 1999 to 2019, then the numbers that we are calculating are what you call extrapolating. So they're using this premise of 90% population or 10% decline. We're kind of assuming that continues. So if I project to like 2050, my numbers are extrapolated, and you have to take them with a grain of salt because you're making assumptions you don't know about. However, if I pick a value between 1999 and 2019, assuming that this 10% decline is actually accurate, those numbers are what you call interpolated. They're coming from within our set of data. Those numbers should hold some weight. They should have some value. You can't expect that they're going to be exact. On any given day, you're going to know exactly how many people, because families are going to emigrate in groups. You're not going to have one person going every time. So it's not completely continuous in that sense, but it gets us pretty accurate results. We also can't really go back to 1909 and expect that this 10% population decay is going to hold true back that far. But we've got a pretty valuable, pretty powerful model here that we can now answer a lot of questions with. So that's where I'm going to stop things today. We've got this new idea of Euler's number E, and we've also got this concept of a natural logarithm, which is really the same as a regular log with a different base. So I want you to try some problems. Page 47, 1 to 3, 4 to 7, 9 and 10, that's your homework assignment. 14 to 16. These are going to be the trickier problems. These are going to be mainly word questions. Those are going to be ones that I'd like you to give a try, but they're not part of your assignment. They're not something I'm going to collect in, okay? But those are going to be the more meaningful problems, if you will. In here, you will find some questions that have some modeling problems, but you will also find a lot of just algebra with logs. So I'm going to end the video now. Hope everybody has a great rest of the day. I will see you all in our chat tomorrow. Please make sure to join if you're able to, because there's some things I want to talk about with the group. So yeah, have yourselves a good night, and I'll see you tomorrow. Bye for now.